Okay, so today we wanted to do with some deep CNN examples. And the first one, which I will start with, is what is called as AlexNet. In fact, like this is credited to be associated with establishing deep learning as a fundamental game changer in vision problems. Now, it essentially started with trying to solve this first problem, which is on ImageNet. So the problem in hand is that of ImageNet. Now, what does it have is pretty interesting. So ImageNet is essentially a data set which has color images, each of size. So this is my color image X. It's a color image, so definitely in RGB format, it's going to have 3 channels, and it has 224 rows and 224 columns. Okay. So every image is of 3 cross 224 cross 224, and it represents any one of the 1000 classes of objects. So these classes can be something like cat, dog, ball, etc., etc. So it essentially represents any one of the 1000 classes of those objects over there. Okay. Now, and you have 1 million such images. So the size of the training set, the number of samples which you have is 1 million, and each image is of size 224 cross 224, and there are 1000 different classes of objects which are present over there. So now this used to be a pertinent problem which was hosted from Fefeli's group in Stanford for quite some time. And then AlexNet came out as a solution around 2008 or 2010, something of that sort. Okay. Now they had a bit of variation, so they were not taking down exactly the way it was supposed to work on. But let me show you. Just a minute. We have the basic diagram. So one thing which they modified was that for AlexNet to work, they changed the size of this image from 3 cross 224 cross 224 to 3 cross 227 cross 227, and then they did not rescale, they just did 0 padding, and they changed it so that this is more compliant with their own architecture which they were using to solve it. That was the point of doing it. Okay. Now what it used to have is something like this, that you have your input X which goes in. This is my input. This goes into a network which has 96 convolution kernels. Now in the base implementation, what they had is something like this: 48 convolution kernels, each of with 11 cross 11 and zero padding and stride of 4. And they had a bank of similar 48 kernels, each of with 11 cross 11, zero padding and a stride of 4. Now they would take these two, they would concat and then get an output over here. Now let us find out what will be the size of this output. So this is my intermediate output, which I call as Z1. Now, with all the information which we had and the way we were solving out earlier, let us try to see what will be the size of this output. So can somebody tell me what will be the size of this output over here? So first and foremost, how many channels do you think will be there?
96.
Okay. So one problem will be what will be the width and height. And this input is this one. 3 cross 227 cross 227.
55 cross 55.
55 cross 55. Okay, so this was my intermediate tensor Z1, which comes to me. Now what I do is I take this Z1 and then I have another set of convolution. So what is that convolution going to be? So I have my Z1. This goes into I have my Z1. This goes into max pooling, and then I have another set of kernels. So this goes into max pool of 3W 2S. So as a result of which I will get another tensor intermediate one over here, which I call as Z2. Now if Z1 is 96 cross 55 cross 55, then can somebody tell me what will be Z2?
96 cross 27 cross 27.
Okay, good. Now that I have gotten that one, now from here I again have a system of two different convolutions. So 128 convolution kernels, each of 5 cross 5 in width. Then what do I do? Then a pad of 2 and just a minute.
Sir, you are on mute. हेलो सर
वो कॉल पे बात कर रहे हैं
राजा कॉल
Oh no, I was not speaking with you guys. I there was a phone call from this my tablet service center. So But I mean, that guy is anyways blabbering. So I thought of finishing my diagram. Now, from here, I do and get my output through another level of channel concatenation, Z3. So now what will be my Z3? So what will be the size of my Z3 now?
256 cross 27 cross 27.
256 cross 27 cross 27. Okay, so now after this one, what we do is we again do a max pooling. Write this one like this. Max pool. So what max pool? I basically have to look and tell you, otherwise I don't remember so many networks. So this is with the window of 3 and stride of 2. And then I end up getting another tensor, which is Z4. So what will be my size of Z4? So what will be my Z4?
256 cross 13 cross 13.
256 cross 13 cross 13. Okay. So now from here, I take my Z4 tensor, which is and then I pass it through again two convolution layers. Convolution layers will be 384 divided by 2. So 192 C 3W 1P 1S and 192 C 3W 1P 1S. Then I put them through channel concat. I get my output, which now I call as Z5. So for Z5, you will now see that it's of size. How many channels?
384.
Okay.
1 cross
384 cross
13 cross 13.
Okay. So over here on top of it, we again run a max pool, which is of 3W 1S. Okay. Now what will be the resultant tensor if I run it with 3W 1S?
384 cross 11 cross 11.
Are you sure? Hey, wait, 3W 1S 1P.
Then 13
Oh,
cross
no,
13.
no. Wait. There is no max pool. So there is again 384. This is basically again the same 192C 3W 1P 1S, then 1C 3W 1P 1S, and then again concat, and then you get your Z6, which is also 384 cross 13 cross 13. It comes out. Okay. Now then you again do a convolution. So again there is a split convolution which is done. And this is 128C 3W 1P 1S and out comes Z7. And what is the size of Z7?
256 cross
256 cross 13 cross 13.
Now,
Sir,
yeah.
I have a question. Like, why are we using the concatenation rather than we can use just 256 cross channel?
No, that's an engineering issue. I will come to it.
Okay.
That's a very pertinent engineering issue. Okay. So what did I have? I had my Z7 256 13 cross 13. So essentially by now the tensor has started becoming like this. This is Z7. Okay, and now I put it through max pooling, and this max pooling is with a kernel size of 3W and with a stride of 2. Okay, so I end up getting another tensor over here. So what will be the size of this tensor? Z8. So Z8 will be what?
256 cross 6 cross 6.
Okay, now what we do after this is you basically linearize. So you get down a set of linear neurons over here. So how many linear neurons will be here in this arrangement?
9216.
9216. So from here you have an FC connection. You have an FC of so essentially there is 9216 FC to 4096. Okay, so over here, how many neurons? You will have 4096. Now you again have 4096 FC to 4096. So you get down another set of neurons over here that will also be 4096. Now from here you have 4096 FC 1000. So this becomes 1000 neurons, and then you have a softmax operation. A softmax operation is essentially what does an argmax on top of it. So whichever has the highest activation, you get that output in favor of that. So this one I can call it as Z8 dashed. This becomes Z9. This becomes Z10. And this is my Y, which is my output over there. Okay. Now let us get back into the reason as to why there was a split. So this is where it all started. So what I did is that instead of taking 96 convolution kernels all together and generating this Z1, I did with the way of taking a bank of 48 kernels and again 48 kernels, then concatenating this one along the channel dimension, input which is Z1 over here. So the question which comes over here is that why do I do that? Now let's analyze this closely.
Sir, you are not audible.
Okay, I was momentarily disconnected. I hope my screen is visible to all of you.
Yes, sir.
So what was this output? 96 cross 55 cross 55. The other option, alternate option can be, let me write it in green. The other option which you have over here is you do something like this. You have your X and you run it through 96C, 11W, 0P, 4S, and then you get your Z1. So tell me something, like in this case, what will be the number of parameters? So if I call this as conv1 and this is conv2. So tell me what is number of params in conv1, what is number of parameters in conv2 equal to. And over here, you need to tell me what is number of parameters in conv equal to. So please tell me in the first case, what will be the number of parameters?
5808.
5808. This will also be 5808. Now what will be the number of parameters in the second case?
$11,616.
11,616. Okay. Was this calculation correct? So how did you arrive at number of parameters?
C into W into H.
Okay, I forgot to add the bias one. So
48 into 3 into 11 into 11 plus 48. That is no.
So 17425. It should have been 17425.
17472. My answer is 17472.
Sir, it is 48 cross 11 cross 11 into 3 plus 1. Right.
Go back to the lecture notes.
Sir, it is 17472.
No, that is what I have written, but others are not telling me as 17472. So what will it be for my other network in green?
34944.
3264.
It's 34944.
34944. This is my answer. Okay. Now tell me something. Is the total number of parameters the same in both the networks?
Yes,
Yes,
sir.
sir. Yes.
Okay. So can somebody tell me what did I gain or lose by just using the first one over the next one? So what did I gain or lose? Did I gain something in the first case or did I lose something in the first case between these two implementations? See, my total number of parameters is the same. Now let us go deeper into it.
Sir,
Now what I want you to do is just don't look into the number of parameters. Also start looking into the space complexity. So you had your X, which went into your two convolutions, conv1, conv2, and say this intermediate what I generate is what I call as Z11 and Z12, and they together are concatenated in order to get down your Z1 over here. Now, can you tell me what will be the size of Z11, size of Z12? So just tell me the size of this in number of elements. I'm not looking into precision of the system as of now. Just tell it to me in terms of number of elements. So can you tell it to me in terms of number of elements?
So zero.
48 cross 55 cross 55.
Z1.
48 cross 55 cross 55. Okay, so how much is that?
145200.
145200. Okay, so now that you have this one created out over here, in the next case, when I have only a single convolution, So what will be the size of Z1 over here? This is going to be 96 into 55 into 55. Now what is that going to be?
290400.
So essentially, the size of these containers over here is also the same. The question which comes out is not related to at all what is the total parameters or the total operational space which is required. What is very critical over here is that you will be able to reslice your operational space. So this is of real critical importance that we are able to reslice the operational space. Now, if I have these many number of elements plus your whatever is the space required to store your kernels, if that is not available within your computer system. So right at the point when AlexNet was getting implemented, the best of GPUs were only limited with about 2 GB of onboard RAM, which meant that they really needed to play out a way such that the total number of parameters and the whole network can appropriately be implemented without compromising on the actual relationship with the parameters, but you need to fit it within the computational requirement of the space over there. Now, that being a very critical point, we need to figure out some ways of doing it out. Now, the way of doing that is essentially by reslicing this whole network into pieces of networks, and that's what we are doing over here.
I have a doubt.
Yeah, tell me.
Sir, so essentially, we are like we are doing the first division into convolution 1 and convolution 2 because of space restrictions on our GPU RAM.
Yes. Yeah.
But then a flip side of this would also be that it will have to do I/O with the main memory, and that will add to the computational time.
Yes, that does add to the computational time. That's the reason why over the generation. Otherwise, why do you think that these GPUs, as we are developing them, why did they come up with better quality RAM infrastructure on top of it? I mean, they could have pretty much done it without that good quality RAM also. Okay. So that's what I had for the day in terms of discussing on AlexNet. Tomorrow we will be discussing quickly about the next network, which is VGGNet, and is the next successor which came after AlexNet in order to solve this problem. And that has a very interesting concept. In VGG, you basically have replicated blocks, which makes it very easier to work it out. So we need to really work out on that mechanism of how can we use these replicative blocks in order to make it simple. So that's the next thing which we will take up tomorrow. And beyond that, I will enter into GoogleNet. And then my plan is that on this Friday, we will have our first hands-on. So tomorrow you will be getting down your instructions on how to really create your machines and be ready so that you can write your first code. And the first level of code which we're going to run is essentially with LeNet as the network.
Okay, sir.
Okay, so that's all for the day. Do you have any further doubts? Okay, otherwise we end for the day.
Thank you, sir.
Yep.
Thank you, sir.
Thank you, sir.